Okay, so we now begin with the pseudo groups. So we introduced what the pseudo group is. So these are sort of elementary definitions of pseudo groups. So we mostly concern ourselves with the classical geometries like Clifford Klein geometry. So this will be concerned with the Lie group acting on a manifold M. So usually, so the Klein's Erlangen program is that the Erlangen program. You have so many G acting on X transitively. So of course, I mean, maybe you can drop this condition, but anyway, so you need some. Maybe both can be dropped, but as a geometry usually sense, you want the transitive and basic action, then the invariant properties on X. Okay. X is the called the GX. So that's called the GX geometry. So we'll be mostly concerned with that. So obvious one is a Euclidean geometry. Okay, so the Euclidean geometry is the where G is the group of motions acting on the Euclidean space Rn. The spherical geometry is one where G is the group of orthogonal transformations acting on Rn. So Sn. So you're looking at the properties which are invariant under this action. So, for example, on Euclidean space, things like length and the angle make sense because they are invariant properties. Okay, and also on the orthogonal space, the same. So you have these properties. So for example, if you have a triangle on the two sphere, then they satisfy some spherical triangle rules and that kind of thing. Uh, so that's what's called the Erlangen program. Okay, so Klein. So actually, so topological manifolds are really a very big category. So there are some really many pathological phenomena in topology, so which nobody really understand completely yet. So we restrict the local property more. So we introduce pseudogroups. So pseudogroups is some way to restrict what we can consider. Okay, so you have some set of homeomorphism. So you have some open set. So this is X, and then so these elements are some homeomorphism U and B. So U and B are of course. So this itself is an element here. Okay, so you looked at all these elements. Pseudogroups is on a topological space is a set of homeomorphism between the open sets. And of course, U and B are important. And so the domains of these elements, so U, all of these U must cover X. Okay, so that means that's needed. And so restriction of any element is also in the element. So if you have some smaller open set U prime, and then the image is V prime, then this element, this restriction is also in the G. Okay, so this is in G, so this is in G. Okay, so that's that. So the composition of two elements are also is in the defined is in G. Okay, so you have two elements. So this means you have some. So suppose we have another one B go to W, then G circle F. You go to W. So this is in G. Okay, so if this is in G, then this is in G. Okay, so those have to be in the. Okay. And of course the inverse. So if you have F, then the F inverse going from B to U. Okay, so those are in the elements. So let if G is a homeomorphism for UV open subsets of X, and so you suppose U is in the union of open sets alpha I. Okay, so alpha in I for some index, and the restriction to each U alpha is in G. Then the G itself has to be in G. So those are the characterizing properties of pseudogroup. So if you have this property, then it's called a pseudogroup. Okay, so it's sort of a bigger set than just looking at self homeomorphisms of X, right? So it's going to be bigger. Okay. So trivial sub pseudogroup is one where every element is just a restriction of identity. So if you restrict identity map, then to all the open sets, then of course that is a pseudogroup, right? Because every property is satisfied, and the pseudogroup contains a trivial pseudogroup. So any trivial pseudogroup will contain trivial pseudogroup because every F has F inverse. So you compose, then that gives you identity. Okay, and so maximal pseudogroup in Rn is top the set of all homeomorphism between the open subset of Rn. Okay, so maximal pseudogroup in Rn is top. So that is the set of all homeomorphism between the open subsets of Rn. Okay. So it can't be any bigger because contain anything. Imagine. So CR pseudogroup is a set of all CR DP homomorphism between open subsets of Rn. Okay, so that's you can verify that's a pseudogroup, and pseudogroup PL or piecewise linear homeomorphism between open subsets. So what is a PL? I mean, PL is the pseudogroup, and the piecewise linear homeomorphism means that any homeomorphism so that you can triangulate the open sets U and V so that it becomes it becomes a simplicial map on that on that uh, on that set. Okay, right. So if you look at all the piecewise linear homomorphism, so here of course piecewise the simplicial division means that you have to be it's a compatible one with the simplices in Rn. Okay, so so of course Rn has a defined simplices, so you don't want to change the simplices in Rn. Okay, so so of course there's a theory of piecewise linear structure, PL structures, but I think we haven't really covered that. But this is an important group also. And GX pseudogroup. So let G be a Lie group acting on a manifold X. Then you can just define the pseudogroup as set of all pair, where U is a set of open subsets, and then so you restrict it to these open sets. Okay. Maybe this isn't so completely right, but anyway, so I keep going. So where is a U is just an open set, I guess I have to recheck it, just an open subset of X. So you look at all the pairs where U is an open set. Okay. So you go through all the open sets of the X. So that's what I mean. And so, for example, isometry group, so which is a rigid motion on acting on Rn, or also orthogonal group, gives you these sort of GX pseudo groups. Okay, and then the G manifold. So G manifold is obtained as a manifold glue with special type of gluings only. So so let G be some pseudo group on Rn, and G, of course, I said Rn, but it could be other manifold X. But G manifold is an N manifold with a maximal G atlas. Okay. So what is a G atlas? So G atlas is a collection of charts where phi going from U to Rn, where U is an open subset of M, such that whose domain cover M and any two charts are G compatible. So So you cover M by these charts, and then they have to be G compatible. So what is G compatible? It means that you take the image of the intersection by phi, and then you send it to the image on the psi of u phi. Then this map phi inverse psi goes from some open set in Rn to open set in Rn, or in X. X is fine. Okay. And so this means it's compatible. Okay. So if you have some maximal correction of this, then this is the going to give you a G manifold. So for any sort of pseudo group, you can define G manifold, or so sometimes this doesn't exist. Okay, so on some given manifold. Okay, so that's the problem. So you can always choose a maximum, a locally finite G address from given maximal one, and conversely. So given a locally finite G address, and you can also get the maximal one, but by just adding them all the uh, compatible ones. Okay? So that's all you have to do to get a maximal one, and of course, you can define G map. So if you have the M and N both G manifolds, and so this is a local homeomorphism, so that F sends a domain of the chart into a domain of the chart. Okay, then this map is also in the groups C. Okay, so F is a element of G locally up to chart. Okay, so that's the definition of the G map. So once you define this G, then there is a whole category of G manifolds, and you can talk about as if this is some sort of category of topological spaces. Okay, so that's how you restrict this set. Okay, so for example, if you just take Rn is a G manifold, if G is any sort of pseudo group on Rn, okay, that's fine, and of course, F is M to N is a local homeomorphism, and if F has a G structure, then so does M, so that the map is a G map. Okay, so so given any local homeomorphism, you can always get. So if one is a G manifold, then the other, you can always get the other one. So you have M. So this is a local homeomorphism, right? That's what I meant. So this is a G G structure, or so I should say G structure means a maximal G address. Okay, maximal. So this is what I meant. So then you can give a G structure here by this local homeomorphism, because so for each of the set so if there's a chart, and then if you send it to another so inside some chart, then you can always get a chart like this, okay, by F. So P circle F, so restricted to some U. Okay, so then you can find the locally finite collection of charts, and then from there you can get the maximal one. Okay, so that's how we obtain. So class of examples such as theta annuli, pi annuli. So I will explain that later on what that means, and so good way to get a G structure is let the gamma be a discrete group of G homeomorphisms of M acting properly and freely, for example. So suppose M has a G structure, and gamma is a discrete group of G self-homeomorphisms. Then the quotient has a G structure, and of course the quotient has a manifold structure, and the chart will be the charts of the lifted open set. Okay. Right. So this is a good way to obtain the G manifolds. So once you obtain it for some open manifold, because it's easy to get a local homeomorphism, and then if there's an action, G action on that manifold, then you can easily get the G structure on the quotient manifold. Okay. So Tn has a CR structure and PR structure because, of course, Rn has such a structure. And Tn, you can think of it as a translation group, right? Quotient by the translation group. And translation group is, of course, CR and also piecewise linear. Okay. So therefore, by the quotient, it will have an induced GR structure, G structure. And so given Gx, Gx manifold is a G manifold where G is a restricted pseudo group. Okay. What I mean is G is a Gx group. Okay, Gx pseudo group. So for example, Euclidean manifold is isom Rn manifold. Okay, so which means that it has isom Rn pseudo group structure. Okay, or pseudo group manifold. So you're just dropping these here. So these are just conventions. What I'm saying. And the spherical manifold is ON plus one SN manifold. Okay.